What if I told you that electricity and magnetism are not two forces at all? That every time you turn on a light, use your phone, or even see the world around you, you're witnessing the same hidden phenomenon at work. Richard Feynman showed that magnetism is just electricity in motion. That light itself is made of electric and magnetic fields dancing through empty space. Once you see this connection, physics stops looking complicated and starts looking inevitable. When Richard Feynman said that magnetism is a consequence of electricity in motion, he was not trying to be poetic, he was pointing to a deep and precise truth about how nature works. An electric charge sitting still creates an electric field around it, and that field exerts forces on other charges nearby. Nothing magnetic appears in this situation, and for a long time, people believed magnetism must be an entirely different phenomenon. But the moment that same charge begins to move, the picture changes. A moving charge produces not only an electric field, but also a magnetic field, and this magnetic influence can push or pull other moving charges. Nothing new has been added to the charge itself. Motion alone is enough to create magnetism. Feynman loved this idea because it stripped magnetism of its mystery. Instead of treating magnets as magical objects with special powers, he showed that magnetism arises naturally from the behavior of electric charges. Consider a simple wire connected to a battery. Inside the wire, countless electrons drift along in one direction. Individually, each electron is just an electric charge, but together, their motion creates a magnetic field strong enough to deflect a compass needle. This field is not coming from the metal of the wire or the battery itself, it is coming from moving electric charge. If the current stops, the magnetic field disappears instantly, reinforcing the idea that magnetism depends entirely on motion. What makes this insight even more powerful is that it works at every scale. Inside atoms, electrons move around nuclei, and their motion contributes to magnetic effects. In materials we call magnets, enormous numbers of electrons are moving and spinning in coordinated ways, producing strong and stable magnetic fields. Feynman emphasized that permanent magnets are not exceptions to the rule. They are simply systems where electric charges are in constant motion at the microscopic level. The everyday magnet sticking to a refrigerator is at its core a triumph of moving electricity. Feynman also pointed out that this connection helps explain why magnetic forces behave the way they do. Magnetic forces only act on moving charges, never on charges at rest. This is not a coincidence or a separate law added for convenience. It follows naturally from the idea that magnetism itself is caused by motion. If there is no motion, there is no magnetism. This simple principle unifies countless observations that might otherwise seem unrelated. Perhaps the most striking part of Feynman's argument is that magnetism is not something extra layered on top of electricity, it is already hidden within it. When electric charges move slowly, magnetic effects are small and easy to ignore. When charges move quickly, magnetic effects become stronger and impossible to miss. In extreme cases, such as particles moving near the speed of light, electric and magnetic effects become so intertwined that separating them becomes almost meaningless. By framing magnetism as electricity in motion, Feynman gave students a way to see the world more clearly. Instead of memorizing separate rules for electric and magnetic phenomena, one could focus on a single idea and explore its consequences. This way of thinking reflects Feynman's larger philosophy of physics. Understanding does not come from piling up facts, but from uncovering the simple principles beneath them. Magnetism, in this view, is not a mysterious force competing with electricity. It is electricity itself revealed through motion. One of Richard Feynman's most mind-bending insights about electricity and magnetism is that the difference between them depends on how you are moving when you observe them. At first, this sounds almost philosophical, but it is a precise physical statement backed by experiment. Imagine two electric charges sitting still relative to each other. From this point of view, the only force between them is electric. They may repel or attract, but there is no magnetic force involved because nothing is moving. Now imagine that you begin to move alongside one of those charges at a constant speed. From your new perspective, the other charge is no longer at rest, it is moving. And once motion enters the picture, magnetism appears. The same physical situation now includes magnetic effects simply because the observer's frame of reference has changed. Feynman used this example to show that electric and magnetic forces are not separate ingredients mixed together by nature, they are different descriptions of the same underlying reality. What one observer calls an electric field, another observer moving at a different speed may describe partly as a magnetic field. The laws of physics do not change, but the way forces are divided into electric and magnetic components does. This idea comes directly from Einstein's theory of relativity, which Feynman loved because it exposed how deeply motion and measurement are woven into physical law. To make this less abstract, Feynman often discussed currents in wires. A wire carrying electric current attracts another nearby current carrying wire. This attraction is usually explained using magnetic fields, but from a different frame of reference. The same interaction can be explained using electric forces alone, caused by tiny changes in the spacing of electric charges due to relativistic effects. The math works out exactly the same. Nature does not care which explanation you use, as long as you use it consistently. What changes is your perspective, not the physics. This realization overturns the idea that magnetism is a fundamentally distinct force. Instead, it shows that magnetism is electricity viewed through the lens of motion. When objects move at everyday speeds, relativistic effects are small, so electric and magnetic forces appear clearly separated. But as speeds increase, the separation becomes less meaningful. Electric and magnetic fields blend into each other, transforming depending on how fast the observer is moving. Feynman emphasized that this was not a trick or an illusion. It is how the universe actually works. What makes this perspective so powerful is that it removes the need for special explanations. Magnetic forces do not require new particles or extra rules. They emerge naturally once you accept that observers in different states of motion measure space and time differently. The deep connection between electricity and magnetism is therefore not an accident of history or notation. It is a direct consequence of how space, time, and motion are structured. Feynman saw great beauty in this idea because it revealed a hidden unity behind everyday experiences. When you watch a compass needle turn near a wire, you are seeing relativity at work, even if the effect is tiny. Electricity and magnetism are not competing forces acting independently. They are parts of a single electromagnetic interaction, sliced into different pieces depending on who is doing the observing. By understanding this, students stop asking why magnetism exists as a separate force and begin to see it as an inevitable result of motion and perspective. This shift in thinking, Feynman believed, was one of the most profound steps toward truly understanding nature. One of the most profound ideas Richard Feynman emphasized about electricity and magnetism is that they do not merely coexist. They actively create each other whenever they change. A steady electric field sitting quietly in space produces no magnetic effects, and a static magnetic field by itself does not generate electricity. But the moment either field begins to change, the story transforms. A changing electric field gives rise to a magnetic field, and a changing magnetic field produces an electric field. This mutual relationship is not a coincidence or a clever mathematical trick. It is a fundamental rule of nature that reveals how deeply electricity and magnetism are intertwined. Feynman often pointed out how revolutionary this idea was when it was first discovered. Before this connection was understood, electricity and magnetism were treated as separate phenomena with their own laws. Experiments showed that moving charges created magnetic fields, but it was James Clerk Maxwell who completed the picture by realizing that changing electric fields must also create magnetic fields, even in empty space where no charges are present. Feynman loved explaining this because it showed how nature values symmetry. If moving charges could produce magnetism, then changing electric fields had to play a similar role to keep the laws of physics consistent. This insight leads directly to a remarkable consequence. Imagine a region of space with no wires, no charges, and no magnets, just empty vacuum. If an electric field in that region begins to change, a magnetic field appears. That magnetic field, as it changes, generates a new electric field, which in turn produces more magnetism. The fields sustain each other, passing energy back and forth as they spread through space. This self-perpetuating process requires no material medium, no hidden machinery, and no additional forces. The fields themselves are enough. Feynman emphasized how counterintuitive this is. We are used to thinking that forces require objects to push or pull on one another. Yet here is a situation where something is happening in nothing at all. The vacuum is not empty in the naive sense. It can support electric and magnetic fields that evolve, interact, and carry energy. This realization forces us to rethink what we mean by space itself. Space is not merely a backdrop where physics happens. It is an active participant. The practical consequences of this principle are everywhere. Electric generators work by changing magnetic fields to produce electric currents. Transformers rely on changing electric currents to create changing magnetic fields that induce new currents elsewhere. Radios, televisions, and wireless communication all depend on rapidly changing electric and magnetic fields that propagate through space. Feynman enjoyed pointing out that these technologies are not exploiting separate laws of electricity and magnetism. They are using one unified set of principles. What fascinated Feynman most was that this mutual creation leads inevitably to waves. Once electric and magnetic fields generate each other in a continuous loop, the disturbance travels outward at a fixed speed determined by fundamental constants of nature. That speed turns out to be the speed of light. This was one of the greatest triumphs in physics, revealing that light itself is an electromagnetic phenomenon. Electricity and magnetism, once thought of as laboratory curiosities, turned out to be responsible for vision, astronomy, and our connection to the universe. Feynman believed that understanding this idea changes how one views physics. Instead of memorizing separate effects, one begins to see patterns and necessity. Changing fields create each other because they must, because the universe would be inconsistent otherwise. In this sense, electromagnetism is not just a collection of facts, but a beautifully interlocked structure. The moment you disturb one part, the rest responds, and from that response emerges motion energy and light itself. When Richard Feynman explained that light is an electromagnetic phenomenon, he was revealing one of the most astonishing unifications in all of science. What we experience as light, something so familiar that we barely think about it, is at its core a traveling pattern of electric and magnetic fields. These fields oscillate together, each continuously giving rise to the other as they move through space. There are no wires, no charged particles riding along, and no material medium required. Light is electricity and magnetism set free, propagating through the vacuum at a precise and universal speed. Feynman loved emphasizing how unexpected this discovery was. For centuries, light was treated as something completely separate from electricity and magnetism. Optics had its own rules, its own experiments, and its own mysteries. Then Maxwell's equations revealed something extraordinary. When electric and magnetic fields change in just the right way, they form waves that move at a speed matching the measured speed of light. This was not a coincidence that could be brushed aside. It was a message from nature saying that light itself is an electromagnetic wave. This realization dramatically simplified our understanding of the universe. Suddenly, visible light was just one small part of a much larger family. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays all turned out to be the same kind of thing, differing only in wavelength and frequency. Feynman enjoyed pointing out that when you tune a radio or heat food in a microwave oven, you are using the same physics that allows your eyes to see. The differences lie not in the nature of the waves, but in how fast the electric and magnetic fields oscillate. What makes this idea even more profound is that it shows how information and energy travel across empty space. When a star explodes millions of years ago, the light reaching your eyes today is a record of changing electric charges in that distant event. Those changes created electromagnetic waves that crossed the vast emptiness between stars and planets without fading into nothing. Feynman found this deeply moving because it meant that the universe is connected by invisible threads of electric and magnetic activity, linking distant events to our own experience. Feynman also stressed that light's electromagnetic nature explains many of its properties without adding extra assumptions. The fact that light travels at a constant speed, bends in materials, reflects from surfaces, and carries energy all follow naturally from the behavior of electric and magnetic fields. Even the momentum of light, the ability of light to push on objects, fits neatly into this framework. What once seemed like separate miracles become consequences of a single unified theory. Perhaps most importantly, this insight changed how physicists think about reality itself. If light is an electromagnetic wave, then what we see is not a direct view of objects, but a response of our eyes to oscillating fields. Vision becomes an interaction between matter and electromagnetism. Color becomes a measure of frequency. Darkness becomes the absence of certain field oscillations. Feynman delighted in showing how ordinary experiences could be traced back to precise physical laws. By explaining light as a manifestation of electricity and magnetism, Feynman showed that nature prefers unity over complexity. Instead of inventing new forces for every phenomenon, the universe reuses the same principles in richer and richer ways. Light is not a special exception, it is the most elegant expression of electromagnetism. And in understanding that, we do not just learn about physics, we gain a deeper appreciation for how a few simple ideas can illuminate the entire cosmos.